Okay. So, if it's okay for you, okay, today after 5:30, so we may have a pause, then we can go on for 1 hour or so, not more than 1 hour, okay? Just to be able to deal with some more issues, okay? And then there's going to be the day after tomorrow, and that's going to be the last lecture. Okay, so if it's okay for you, we can have 1 extra hour today, right? If you wish, okay? Right, so let's recall the main things we have learned last time. Last time we defined the mathematical background for introducing pure supergravity. Okay, first of all, we want to define supergravity as the gauge theory of a super Poincaré group. So a theory which is locally invariant under, or invariant under local super Poincaré transformations, and therefore we have introduced the relevant fields as connections, okay, in a bundle, okay, whose structure group is the super Poincaré group. Okay, so we have defined a connection one form whose components along the super Poincaré generators are the relevant fields. That is the field bind, the connection, the spin connection one form, and then the Gravitino one form, okay? Mu and mu, okay? The Gravitino one form. Gravitino one form, which is the gauge field of the associated with the supersymmetry generators, right? Kappa is the Newton's constant. Okay? We computed from this the curvatures, as usual, okay? Curvatures and the corresponding Bianchi identities. A tilde A mu, we have identified it with V minus V mu A, right? The curvatures are defined this way. Well, here we can use the collective symbol A tilde capital A for denoting all the one forms here, okay, and TA the corresponding generators, right? Then we define the curvature, two form, which has value in the super Poincaré algebra, and this I write as RA TA, where RA is equal to dA tilde A plus C BC divided by 2 A tilde B wedge A tilde C. Okay, that's the general formal expression for the curvatures. Okay, then RA is minus TA. So TA, call it tilde because it's the super torsion. Here, I read it off here, from here, and that's dVA, or better, dVA, Lorentz covariant derivative, okay, plus I k squared divided by 2 psi bar gamma A psi. Okay? This is the definition of super torsion. And then we have definition of the usual definition of the Riemann tensor, and the curvature associated with the gravitino field, okay, which is d psi, namely d psi plus omega AB divided by 4 gamma AB psi. Today we are going to deal with the gravitino and with the description of its dynamics. Okay, we also have the Bianchi identities, namely dRA equals dRA plus CBCA A tilde B wedge RC, and that's equal to 0. Okay, from general arguments, that's simply equal to 0. And this implies in particular that d t tilde A, which is equal to, so d, this is the total derivative with respect to all, covariant derivative with respect to all the generators, right? So all the connections here. That is dTA plus omega AB wedge T tilde B. And this is the Lorentz covariant derivative, okay, which we denote without a tilde, d tilde T tilde A. And then we have minus RAB wedge VB plus I k squared psi bar gamma A rho, okay? And this is equal to 0. Okay, this is the Bianchi for the super torsion. Then we have the usual Bianchi for the Riemann curvature. AB, but that's the usual Lorentz covariant derivative. Okay, that's the usual Lorentz covariant derivative, and that's equal to 0. And finally, we have d tilde rho, which is d rho, and that is equal to RAB. Okay, that's d squared psi, okay, because rho is the covariant derivative of psi. D squared of psi is nothing but RAB gamma AB divided by 4 wedge psi, okay? And this is the Bianchi identity for rho, the curvature of psi, okay? Good. Now let's move to the definition of the gravitino field, okay? And the description of its dynamics. How do we define the gravitino field? Here, the gravitino field is just the one-form connection associated with the one-form gauge field associated with the supersymmetry generators. Okay. Apart from the form index mu, okay, psi has the same quantum numbers as the corresponding supersymmetry generator, right? So psi, it has a mu and an index alpha, okay, where alpha underscore runs from 1 to 4, and so labels the spinorial representation of the Lorentz group. That belongs to 1/2 with respect to the Lorentz group, which corresponds to the index mu, the vector index, okay? This is the vector representation of the Lorentz group times 1/2 0 plus 0 1/2. Okay, should be familiar with this notation. Okay, then what this is. Let's start with the flat space. Okay, so we start with the description of psi in flat space. Then we move to curved space, right? What this is 3, so 1, 1/2 plus 1/2, 1, okay? And that's the spin 3/2 representation, plus 1/2, 0, plus 0, 1/2. This is the spin 1/2 representation, okay? Now, psi is an elementary particle, so it should correspond to an irreducible representation of the Poincare group, okay? Which one? This one, okay? So this is a spin 3/2 representation of the Lorentz group, okay? And this is a spin 1/2. This is the representation describing our gravitino field. This is a spin 1/2 component, and we can get rid of this component by setting gamma A, which is gamma mu psi mu equals 0. Okay, this is a gauge choice. Yes. In an irreducible representation. Well, this is an unfortunate notation, but it's common in all field theory books, because you're actually, this is an irreducible representation of the Lorentz group, but you describe the Lorentz group as the Lorentz group is O 1,3, right? Now you describe this as SL2C. Okay, then you describe SL2C as the product of two SU2, if you want. That's not true, okay? But in the complex field, okay, so if you complexify this group, okay, then you can write the algebra as the direct sum of two SU2 algebra, okay? So that's just a simple way of describing representations of the Lorentz group, right? So actually this corresponds to describing this object, this group here, somehow as a product of two SU2, okay? But this should be regarded as an irreducible representation, right? Of the Lorentz group, just as this one, okay? How do you define? How do you see these two components? Okay, these two components. Well, these two components are the Weyl components of the spinor, right? The Weyl components of the spinor. Now, the Weyl components of the spinors, okay, they are not irreducible representations themselves of the Lorentz group, but only of the component of the Lorentz group, which is continuously connected to the identity, okay? What happens is that the Lorentz group is bigger. The Lorentz group contains parity, contains time reversal, contains transformations, okay, which map this into this, right? So you can see it in another way. These are reducible with respect to the identity sector of the Lorentz group, SO, but not with respect to O, okay? Because the Lorentz group is bigger, contains transformation which maps this into this, right? The parity, we know parity transformation, what's the effect of it, okay? Sorry?
This trick works in 4 dimensions.
In odd dimension it doesn't work. You don't have chirality there, in odd dimensions, okay? So that's another way of seeing this, okay? Okay, so this is the then the field, the spin 3/2 field, satisfies the Rarita-Schwinger equation. Which is an equation for a spin 3/2 field. Okay, here we consider the massless spin 3/2 field. The equation reads epsilon mu nu rho sigma gamma nu d rho psi sigma. Remember, for the time being, we are in flat space time. Okay, equals 0. Now this is massless and has a vector index. Okay, there are longitudinal modes which are unphysical, and you want to decouple them. Okay, in particular, there are gauge transformations associated with this field here. If you redefine, if you transform psi like this, okay, namely you perform a gauge transformation, a gauge transformation on psi, the equation is invariant, as you can easily verify. Okay, so these are non-propagating components of psi mu. These are gauge components of psi mu, longitudinal if you want. But longitudinal components of a spin 3/2 field are described by a spinner. Lambda is a spinner. Lambda is a spinner. So how many chirality components does a spin 3/2 field have? Well, it has plus or minus 3/2, plus or minus 1/2. Okay? But a massless one, in a massless one, the plus or minus 1/2 components, they are gauge, and they can be gauged away. So that the only propagating degrees of freedom correspond to the two helicity components, plus or minus 3/2. So these are the only helicity components of a propagating gravitino field, spin 3/2, massless spin 3/2 field. Okay? Just two components. Okay. Now we wish to generalize this description to curved space-time. Okay? So remember, a consistent description of a spin 3/2 field requires invariance with respect to this gauge transformation, which allows to decouple the gauge components from the physical field. Now, what happens in curved space-time? Well, in curved space-time, this group theoretical characterization refers to local Lorentz, the Lorentz which is defined pointwise in each point in space-time. Okay, how do we adapt this description to a curved space? Simply by making it invariant under a general coordinate transformation, generalized coordinate transformations, and this is done by promoting ordinary derivative to covariant derivatives. Okay? Ordinary derivatives by covariant derivatives. Covariant derivatives with respect to which connection? Well, the connection we have at our disposal, okay? So in general, our choice would be to define in the equation, the field equation, okay, the covariant derivative, okay, as a derivative which is covariant with respect to all the indices of psi, namely mu and alpha, which I have omitted here, okay, spinorial and vector index. So in principle, we would write something like that, plus 1/4 omega AB, gamma AB, mu psi nu, plus minus actually gamma mu nu rho psi rho, where this is the Christoffel symbol. Okay. Let's call this part of the covariant derivative without the Christoffel symbol by a curly d symbol. So this reads d mu psi nu minus gamma mu nu rho psi rho. Okay? Now, this quantity appears in the field equations anti-symmetrized in the two indices, in the derivative index and in the gravitino index, anti-symmetrized. Okay? Now, it turns out that the most appropriate choice for the construction of the supersymmetric action, okay, is to replace ordinary derivative not by the most general covariant derivative, which I've written here, but just by the covariant derivative with respect to the spin connection, omitting the Christoffel symbol. Why? The reason is that if we also insert the Christoffel symbol in the definition of the covariant derivative, then supersymmetrization becomes much, much more involved. But do we lose something? Actually, we don't lose anything. Why? Because if we anti-symmetrize this quantity in its two indices, this is d mu psi nu plus minus gamma mu nu rho psi rho, which is nothing but d mu psi nu minus 1/2 t mu nu rho psi rho, where t is the, remember, t is the curve, is the torsion tensor. Okay, so this quantity is covariant as well as this one. Okay, both quantities are covariant because they differ from one another, okay, by a tensor. So we can choose both, actually. In order to make the field equation covariant, we can use both of them. They differ by a tensor, okay? So both of them, they serve our purpose of defining the field equation in consistently in a curved space-time. However, if we use this, then the path to supersymmetrization is easier. Okay, so let's use this, and we write. Sure.
So the spin connection and the Christoffel symbols they are independent.
Well, you remember how they are defined. They are different, of course. Yes. They are one defines the action of the local Lorentz on spinner. So yeah. No. That's just this is just for general coordinate invariant with respect to general coordinate transformations, okay, of vectors in a coordinate basis. Okay, so actually, if you want, these two are two different description of the same thing because they are related by the condition that, do you remember, the vanishing of the torsion in our spacetime, and this if you want, allows you to define omega in terms of v and gamma in terms of v as well. Okay, if torsion vanishes, of course. Okay, otherwise they are both expressed in terms of v, its derivative, so the field bang, its derivative, and the torsion. Okay. But these are connection with respect to local coordinate transformations, okay? And this expresses the action of the connection on the spinner, right? So epsilon mu nu rho sigma can be written as, gamma nu. Well, the equation can be written then in the following form, equals 0. Okay? And this is now covariant, fully covariant. Okay? This is now fully covariant. Or if you want, equivalently, as gamma mu d nu psi rho equals 0. Now, you can verify some properties. First of all, if we use the gauge condition gamma a psi a equals 0, then each component of psi satisfies the Dirac equation. Gamma mu d mu psi nu equals 0. Okay? This you can easily verify by contracting this equation by means of gamma mu nu. You contract this equation by means of gamma mu nu, okay? And then you do some algebra. And what you end up with is the following. Gamma nu d nu psi mu equals d mu gamma nu psi nu. Okay? You end up with this equation here. But this is d slash psi mu, okay? And if this is true, then this is 0, okay? Then, yes. No, A, I'm sorry, it's A. It's Lorentz covariant, okay? There are two ways of writing it. Remember, gamma A are the gamma matrices associated with the local Lorentz field and are constant matrices, okay? Constant matrices. Gamma A, gamma B equals twice eta AB. These are constant matrices. However, we still define gamma mu. How? Simply by contracting with the inverse Filbine. Okay, so now you see gamma mu depend on X through the Filbine matrix, okay? And they satisfy gamma mu, gamma nu equals twice G mu nu of X. Okay? So when I write gamma mu in curved space, I refer to gamma matrices depending on space-time through the Filbines. There is a Filbine inside. So even when you do derivatives, okay, you have to take into account that gamma mu now are local quantities. Okay? They do depend on space-time, and therefore derivatives act on them. That's why it's important, well, it's convenient to write all equations for the various fields in curved space in terms of rigid Lorentz indices, A, simply because gamma A are constant. Okay? And all the properties that we know for gamma matrices in flat space-time, they simply apply to the gamma A matrices. You can also verify that G mu nu, D mu psi nu equals 0 in the same gauge choice. okay, for the same gauge choice. Because you can verify that G mu nu, d mu psi nu, that is equal to gamma mu d mu times gamma rho psi rho. Okay? And that is 0 if we use this gauge choice. Okay? Okay. Finally, also gamma mu nu d mu psi nu is 0. Okay? Also, this is 0. You can easily verify. Okay. Can we deduce this equation, the Rarita-Schwinger equation in curved space that we have written just now? Gamma mu d rho psi sigma equals 0. Can we deduce it derive it from an action? Yes, we can. Let's write the action. The Rarita-Schwinger action reads epsilon mu nu rho sigma psi bar mu gamma 5 gamma nu d rho psi sigma. Okay? If you vary with respect to psi, take into account that psi are Majorana spinors. Okay? So these two are not independent. Okay? When you derive. Okay, if you derive with respect to psi, what you get is precisely Rarita-Schwinger equation. And this can also be written in this equivalent form, i.e. psi mu bar gamma mu nu rho d nu psi rho. Okay, d mu nu psi rho. This you can check. Where we have used the definition of gamma 5, okay? Remember how gamma 5 is defined and properties related to gamma 5. Remember the very definition of gamma 5. Gamma 5 is equal to I epsilon A, B, C, D divided by 4. Gamma A, B, C, D. Okay? Rigid indices, so constant matrix. Rigid indices, so constant matrix. Sure. I. Here, IE, yes. I'm sorry. Yes, E is the determinant of V mu A. I'm sorry, yes. Okay, that's the usual thing that occurs in Lagrangian, in actions, okay, in curved space. Okay. That's E. So if you write, for instance, gamma 5, gamma A, that is equal to epsilon minus I, epsilon A, B, C, D, divided by 3, factorial gamma B, C, D. Okay? Now, if you change all these indices to curved indices by using the Filbine, okay, then gamma 5 gamma mu, what is this? This is V mu A gamma 5 gamma A. Okay? I'm changing the index A rigid into curved index, right? And I'm turning gamma A into gamma mu. Okay? What is this? Well, this is, I write this in this form here, 3 factorial, V mu A, epsilon A, B, C, D. Okay. Then I want to change also these gammas to curved gammas with curved indices. Then I have to do the same thing for each of these indices. So V nu B, V rho C, V sigma D, gamma nu rho sigma. Okay? Gamma nu rho sigma. Now, what is this? Matrix theories, theories of matrices. This is nothing but epsilon mu nu rho sigma times the determinant of the matrix V, which is E. So, here I get minus I E over 3 factorial epsilon mu nu rho sigma gamma mu nu rho, nu rho sigma. Okay. So you can easily change here in all these relations rigid indices, okay, by curved indices, taking into account that you always have to associate with each epsilon a measure, okay, the determinant of the matrix, a characteristic factor. Okay, epsilon mu nu rho sigma is the same as epsilon A, B, C, D. They are just numerical tensors, okay, numerical quantities, not tensors, but numerical quantities. The entries are numbers. So epsilon 0, 1, 2, 3 is equal to +1. Okay? Either if we regard 0, 1, 2, 3 as curved indices or rigid A, B, C, D indices. Okay? It's always +1. It's always +1. Okay? So this means that E epsilon mu nu rho sigma, if we raise all the indices mu nu rho sigma by means of the matrix, the inverse matrix, what I end up with is 1 over E epsilon mu nu rho sigma. Okay? Because you get the determinant of the matrix. Okay. Now it is useful to write the action we have just derived here, this action here, or if you want this, in terms of forms, okay? Namely as a 4 form, okay? As a 4 form in our 4-dimensional space-time. So we define L Rarita-Schwinger 4 as a 4 form. How do we write it? Well, it has this very simple expression, gamma 5, gamma A, d psi VA. Okay? You see, it has this very simple expression. Notice that we are using gamma A. Okay? So the gammas with the rigid index, which are constant matrices. Okay? And also gamma phi is a constant matrix. Why is this equal to this? Okay, what's the relation? Well, we simply write all the forms in a coordinate basis. Okay, and then see what happens. That's minus psi mu bar gamma 5 gamma A d nu psi rho. Okay. Let me also, okay, fine. And then VA sigma dx mu wedge dx nu wedge dx rho wedge dx sigma. This is this 4-form Lagrangian written in form notation, in the notation of exterior forms. What is this? Well, remember now that VA sigma times gamma A is gamma sigma. So this is nothing but sigma, d rho psi, d mu psi rho. Okay, what is this? dx mu dx nu is something which is totally antisymmetric in mu nu rho sigma. We are in 4 dimensions. It can only be proportional to epsilon, the epsilon tensor, the epsilon symbol. Sorry, epsilon is not a tensor. Okay, epsilon symbol. We define d4x as dx not dx1, dx2, and dx3. But that is equal to epsilon with a minus 0, 1, 2, 3 d4x. Okay? Because remember, 0 with the upper indices is minus 1. So this means that dx mu wedge dx mu, dx nu, dx rho wedge dx sigma is equal to minus epsilon mu nu rho sigma d4x. Okay? Let's write it here. What we get is plus epsilon mu nu rho sigma d4x. Okay? Right? And now we just take this sigma here, okay, and then we write the action just as we wrote it before, namely epsilon mu nu rho sigma psi bar mu gamma 5 gamma nu d rho psi sigma d4x. Okay, d4x. And that's it. Okay, now consistency of this description requires invariance with respect to with respect to gauge transformations associated with the gravitino field. Now, in flat space-time, these were of the form, of this form, okay, in flat space-time. Now, they clearly generalize to curved space-time by changing the ordinary derivative by covariant derivative, okay? Now you can easily verify that the Rarita-Schwinger action is not invariant with respect to this transformation. Yes?
On the top line, the D has its rho, and there the D has its
Here? Yes. I just performed a change in the index position here. I took this this sigma, and brought it here. There are two inversions, which is a plus. And then I renamed the indices. Okay? Is it okay? No. So let me just take this nu here. Okay? Let's do it. Let me take this nu here. Nu, sigma nu rho. If you make two inversions, you get a plus. Okay? Now, the first index is contracted with the first index of the epsilon. The index of the gamma is contracted with the second index of the epsilon. The index of D is contracted with this, and the index of psi is contracted. So they are just the same. They're just dummy indices. Okay. Okay. Now you can easily verify that this transformation here is not a symmetry of this action. So this description is inconsistent, simply because we cannot decouple. We are not able to decouple the gauge modes, the longitudinal modes from psi. And these longitudinal modes, they are unphysical. So a consistent description of gravitino requires invariance with respect to this gauge transformation. But this gauge transformation is called supersymmetry. Why? Because it is a local symmetry, a local transformation, local symmetry parametrized by a symmetry parametrized by a local spinner. The local spinner which talks to the longitudinal modes of psi, okay? Which parameterize the longitudinal modes of psi. So this is telling us that the Rarita-Schwinger action by itself is not supersymmetric. Okay? As we are going to see in a moment, we need, in order to make the whole description supersymmetric, and therefore the description of our gravitino consistent, we need to couple it to the graviton. Okay? We need to couple it to gravity. Only coupling gravitino to gravity, we can make its description consistent. Okay? And that is, we can construct a supersymmetric theory. In order to describe gravity, okay, we are going to use the first order notation, or Palatini notation. Are you all familiar with this? Palatini notation, first order description? 1, 2, 3, 4, 5. The other? So and so. Let's review. Let's review it for a moment, okay? Yes?
In the last expression in there, I was expecting kind of a square root of g factor in front of it.
No. No. You get the square root of g only if you change gamma 5. The square root of g is inside gamma 5. Remember how gamma 5 is defined. The square root of g is inside it. So somehow, if you change this in the other formulation, okay, then you get gamma 5. Okay? If you eliminate gamma if you eliminate gamma 5, then you get the factor e. Okay? Okay. So, let's review the first order description of gravity. Okay, that is the Palatini description of gravity. Of general relativity. Okay, you all know that general relativity is described by the Cartan-Hilbert action. Where R is the curvature scalar and E is the square root of the absolute value of the determinant, okay, of the metric. Okay, now this we can write as minus 1 over 4 kappa squared, and this I invite you to verify, RAB wedge VC wedge VD epsilon ABCD. Okay, so far we haven't used any first order description. Okay, so far we have just rewritten the Einstein-Hilbert action. Okay, why is it so? Because RAB, wedge VC, wedge VD, epsilon ABCD, that is equal to RAB EF divided by 2, VE wedge VF, and here I've just written the curvature tensor times VC VD epsilon ABCD. That is equal to RAB EF divided by 2 times VE VF VC VD epsilon ABCD. But what is this? This is the product, wedge product of 4 gammas, 4 V's, 4 Vielbein. And therefore it's proportional to epsilon EFCD times the determinant of V, which is E, with a minus sign. So there is minus E divided by 2 R A B E F epsilon E F C D epsilon A B C D. Now you use the properties of epsilon symbols, and you get what do you get? You get minus 2, sorry, plus 2, and then you get a delta. R, E, F, or AB, EF, delta, EF, AB, which is twice R, the curvature scalar, right? Okay, now, what does this first order formalism consist in? Well, in the first order or Palatini formalism, we treat VA and omega AB as independent. Okay? We impose no torsion equation to start with, okay? They are independent fields. R depends on omega, and the action depends on V through these quantities, through these factors. Okay. So we start considering these two fields as independent. Then we deduce from this action here, from the Einstein-Hilbert action. Okay, we vary the action with respect to VA and omega AB, and we determine the corresponding field equations. And we'll see that the field equation corresponding to omega obtained by varying with respect to omega AB is nothing but a torsion equation, which will allow us to express omega in terms of V. Okay, let's see how it works. Remember that if we have a general curvature that we have written as dA tilde A plus C BC A tilde B wedge A tilde C divided by 2, and we vary with respect to A, okay, then RA, so we do A R varies by a covariant derivative of the variation of the connection. Okay, that you can easily verify from here. Okay, and this is nothing but the covariant derivative with respect to all the connections. And this clearly holds also for the Lorentz group, okay? Also for the Lorentz group. So if we vary omega AB by an infinitesimal amount, what happens is that RAB varies by the covariant, the Lorentz covariant derivative, which we have denoted by curly d with no tilde, of delta omega AB, which is nothing but d delta omega AB plus omega AC wedge delta omega CB minus omega BC wedge delta omega CA. Okay, that's easy. Okay, now let's take the Einstein-Hilbert action written in terms of forms and their exterior derivatives, and vary it with respect to, so S variate with respect to omega AB. Omega AB is just inside here. Omega and V are independent now, first order. So the variation of S is minus 1 over 4k squared. Delta omega, so D, delta omega AB, wedge VC, wedge VD, epsilon ABCD. Okay? Now, I integrate by parts. Total derivative minus the rest. And we neglect the total derivative, okay? Because we are neglecting boundary terms. So this is equal to delta omega AB with a 2, wedge DVC, wedge VD, epsilon ABCD, okay? Why there is this 2? Because if I integrate by parts, then the derivative hits here and hits here. But it gives two equal terms. Okay, so I just write the two terms as twice on the term in which I simply derive the first of the v's. Okay, and there's no minus sign because delta omega is a one form. Okay, so when I pass through delta omega by means of delta d, I get a minus sign. Okay, you do check. Next, we compute the field equation. And what do we expect to find? Well, delta S we find d VC wedge VD epsilon ABCD equals 0. What is this? What is this? Well, this is nothing but, remember, TA, the torsion. The torsion, not the super torsion, because we haven't coupled gravity to the gravitino yet. Okay? That's the torsion. So this implies TA equals 0. This equation is a torsion equation, and we have derived it in the first order formalism as the field equation with respect to omega AB. And this allows us to express omega AB as a function of V. Okay, as you can easily do. So, solving this equation, you see this equation is algebraic in omega. So omega has no propagation. Omega is an auxiliary field, okay? Non-dynamical field. This equation is solved simply by expressing omega in terms of V. And so we are back to the second order formulas. Then what happens if we derive with respect to V? What's the derivative with respect to V? Well, delta S over delta V, A equals 0. Here we get R AB. Let's do it with respect to VD, okay? Wedge VC, epsilon ABCD equals 0, okay? I just drop the final one, for instance, okay? This is the derivative of S with respect to the field by one form. Okay, what is this? To understand what this is, I compute the wedge product of both sides with respect to VG, another index which is not there, VG. Okay, where G is another index which has nothing to do with the indices here. What we get? We get RAB, wedge VC, wedge VG, epsilon ABCD, okay? That has to be 0. Now you do the same derivation as we did before. Now take into account that G and D are different, different indices. What do we get? We get R A B E F delta E F G A B D, where this is the totally antisymmetric delta symbol. Okay? Delta E F G A B C is equal 1 over 3 factorial delta A E F G delta E A delta F B delta G C plus permutations with the appropriate sign. Okay? Okay. And what is this contraction? This is nothing but, this contraction is nothing but the Einstein equation in the vacuum, namely 0 equals, so it's minus 2, which we don't care, R GD minus 1/2 delta GD R. Okay? But this is an Einstein equation in the vacuum, namely RAB minus 1/2 eta AB R. Einstein equation written in the rigid indices. Okay? Okay. So, equation with respect to omega AB, torsion condition. Yes? Is it equivalent? Sorry, Sue? Of course, of course, of course. Yes, because these are all tensors. So I can simply contract both sides by VA mu, VB nu, okay? And I get R mu nu minus 1/2 G mu nu R equals 0. And this is Einstein equation in the vacuum. Okay, but now we want to couple this action, okay, to the gravitino and show that we can make the whole action supersymmetry invariant, and namely we can derive from it a consistent description of the gravitino field. So let's now simply add to the Einstein-Hilbert action the Rarita-Schwinger action. And we get minus 1 over 4 k squared RAB VC wedge VD epsilon ABCD, okay, minus psi bar gamma 5 gamma A d psi VA, okay. Remember, this was our description of the action of the Rarita-Schwinger action, okay, in form notation. Okay, so we are in the first order formalism. So VA and omega AB are independent. Okay, first order formalism. What do we do? Well, we just proceed as we did before. We compute the field equations with respect to the three fields. Now we have three fields: VA, omega AB, and psi. Let's compute first the field equation with respect to omega AB. L4 is equal to minus 1 over 2 kappa squared modulo total derivatives, which I'm ignoring systematically. Modulo total derivatives, remember the first term can be written as delta omega AB wedge D VC wedge VD epsilon ABCD, okay, plus plus. Now, where's omega AB inside here? In D, okay? And to take it from here to here, okay, we have to pass across psi. And that gives us a minus sign, okay? Because two forms anti-commute. So we have a plus delta over 4 delta omega AB psi bar gamma 5 gamma C gamma AB psi VC, okay? Okay, now we are ready to eliminate omega because we have taken omega to the leftmost end of our Lagrangian. Okay, now you can simply drop it. Let us write gamma C gamma AB as gamma A CAB plus twice eta CA gamma B. This is anti-symmetrization AB. You can easily verify that this is true. Okay? So, what do we get? We get an equation which has the following form. dVC wedge VD epsilon ABCD equals k kappa squared divided by 2 psi bar gamma 5 gamma C gamma AB psi, okay? VC. And this, using that formula there, is equal to, then remember that this is also I epsilon CAB D gamma 5 gamma D plus twice eta CA gamma B. Okay? I've used here. Yeah.
How much does the wedges and the epsilon? So, for example, the next term should be contracted with epsilon. Could you just look it over and see where the wedges should be?
Oh, I'm sorry. I didn't write the wedges. Yeah, and the wedge here. I'm sorry. Yes. So between each form, there's a wedge product. Okay. Sometimes in writing expressions containing more forms, I may skip some wedges. Okay. But thanks. It's important to write wedges. Okay. I will tell you at some point from now on, I will neglect all wedges. Okay, and leave you as an exercise to put the wedges. Okay. Okay. Good. Then what happens here is that I get I kappa squared, okay, divided by 2, epsilon A, B, C, D, psi bar, gamma D, psi, V, C, wedge, wedge, wedge. Okay? Okay. Okay. And then we have also this term here. Okay? Okay? But that term there, let's write it down, plus kappa squared, because I have 2 here, 2. And then I have psi bar, gamma 5, then I have eta AC, gamma B, psi, eta AC, anti-symmetrized, VC, okay, which is nothing but VA, okay, if you want. Now, what's wrong with this? Well, this is 0. This is 0. Why is it 0? By a property of the psi forms. Let's check. if I have a bilinear, a psi bilinear of this form here, where here there is a gamma matrix, okay, any, okay, psi with a wedge, okay. If I have a psi bilinear like this, I remember that psi is a Majorana spinor, okay. So this I write as psi transpose C gamma psi, okay, with a wedge. Now, what happens if we interchange psi and psi transpose, okay? That I can do. What happens? Well, psi has, each psi have an alpha index, okay, if you want, which is a spinor index. Alpha index, which is a spinor index. But then it also has a form index. And it is anti-symmetrized in mu nu, because they are forms, and they are anti-symmetrized in their form index, because there's the wedge product. Okay? So what happens if we switch the position of the two? Here we get minus, because we are switching to spinorial quantities, beta, nu, psi alpha mu, anti-symmetrized in mu nu. Okay, but then I can restore the position of the space-time indices with another minus sign. So I have plus, okay? So if I switch the position of the two, these two psi, I get a plus. Psi as one forms, they commute, because you get a minus sign from the fact that they are spinors, and another minus sign from the fact that they are one forms. And if I switch the position of two one forms, I get another minus. Minus times minus is a plus. So what we get here is psi transpose C gamma transpose psi, because I've just interchanged the position of the two psis. Okay? So this means that this quantity is non-vanishing only if C gamma transpose is equal to C gamma. Namely, C gamma, C times gamma, is a symmetric matrix. Okay? Is a symmetric matrix. You can easily verify, and I leave it to you as an exercise, that C gamma mu 1 mu k transpose equals to minus 1 to the k times k plus 1 divided by 2 C gamma mu 1 mu k. You can easily check this. Okay? So for instance, k equal to 1 is antisymmetric. So k equal 1 is symmetric. It's symmetric, so it's okay. It can live between two psis. Okay? 2, yes. 3, no. 3, no. And 4, that is equal to 0, no. Okay? Because the corresponding matrix is antisymmetric. So, psi bar gamma 5 gamma a, okay, that since gamma phi is the product of 4 gammas, okay, this is the same as gamma with 3 indices, right? And this is 0. Because we do, the one with gamma with 3 indices is antisymmetric, okay? Similarly, psi bar psi is equal to 0, because the C symbol is antisymmetric, and psi bar gamma 5 psi is equal to 0. And this we can use. And this simplifies this equation, so this goes to 0, and what we end up with is the following. D BC wedge VD epsilon A B C D equals I kappa squared divided by 2 epsilon A, B, C, D, psi bar gamma D, psi VC. Okay? Well, let me put a minus here and interchange these two. Okay. Okay? I take away all the epsilon for the common factors, and then I get dVA equals minus I kappa squared divided by 2 psi bar gamma A psi. This is the equation for omega. This is the equation for omega. Okay? You see, now the torsion is not 0, but it equals a current in the gravitino field. Okay? What is 0 is not the torsion, but what we call the super torsion. Okay? The super torsion. T tilde, remember, A, which was dVA plus I k kappa squared divided by 2 psi bar gamma A psi. This is what we call the super torsion. Okay, in our geometrical description of local Poincare invariance. Okay, this is 0. This is an algebraic equation for omega, which allows us to express omega in terms of all the other fields. But you see, now we have a torsion. Omega is not only a function of V, the field bind, the matrix, but also a function of psi. So this is a torsion full. This is a torsion full connection, okay? Very good, and what is the torsion? Remember, TA is dVA, which is TA mu nu divided by 2 dx mu wedge dx nu. And this is equal to minus I kappa squared divided by 2 psi bar gamma A psi. Okay? This is the torsion tensor that we have defined at the beginning. So its components are just TA mu nu, which are equal to 2V rho A gamma rho mu nu, okay, where gamma are the Christoffel symbols. And this is nothing but minus I kappa squared psi mu bar gamma A psi nu. Okay? This is the torsion. You see, the torsion is a bilinear in the spinorial field, in the gravitino field. It is useful to express omega AB, solution to this equation, as a sum of a torsionless quantity, plus the rest, delta omega AB. Okay, where this guy here is solution to dVA plus omega AB as a function of V, wedge VB equals 0. Okay, the torsionless quantity is function of this equation, torsion equal to 0, and this guy here, simply plug this here inside this equation, which is an algebraic equation for omega, and I derive delta omega AB. I leave it to use an exercise to derive delta omega AB, which is equal to minus I divided by 2 kappa squared times psi c bar gamma A. Let me write delta omega with all indices down. A, C, A, B. Gamma A, psi B, plus psi bar A, gamma B, psi C, minus psi bar B, gamma B, C, psi A. Okay, you try to derive it. If you have problems, you just ask. Okay, try to derive from this equation, okay, the expression of delta omega B. Okay, any question? Okay, then we can solve this equation. Okay, we have the torsion full connection. We just plug it in our action, and then we compute the equations of motion for all the other fields. Okay. For instance, the equation of motion with respect to the field bind. What is it? Well, delta L4. Just check. That is delta VA minus 1 over 2 kappa squared R BC VD epsilon A B C D plus psi bar gamma 5 gamma A D psi. Okay, this is the equation for VA. That gives us R AB wedge VC epsilon A B C D equals minus 2 kappa squared psi bar gamma 5 gamma A D psi. Okay? On this side, we know there's going to be the Einstein tensor, okay? While on the right-hand side, we're going to have the energy momentum tensor of the gravitino field. You do it the same way we did it in the pure gravity case, okay? And what we end up with is R mu nu minus G mu nu divided by 2 R equals minus kappa squared divided by E, okay, epsilon rho sigma delta mu psi rho bar gamma 5 gamma nu d rho sigma psi delta. Okay, so this is the energy momentum tensor of the gravitino field. It's a straightforward calculation. Okay, it's a straightforward calculation. I leave it to you as an exercise. Okay, very good. So the Rita-Schwinger equation. That's the final equation. Delta psi, that's obtained by varying the action with respect to delta psi. Okay. And what do we get? Delta psi L4 is equal. Yes? Any questions? Sorry? There's a mu here and a nu here. Mu nu. And you can check that it's symmetric in mu nu. Okay? And here I get delta psi bar gamma 5 gamma A d psi VA plus psi bar gamma 5 gamma A d of delta psi VA. Okay, you vary psi. You have to vary both psi's because they are not independent. They are Majorana spinors. Okay, you vary both of them. And what do we get? You integrate by parts the last one, the last term here. Okay, and so we have delta psi bar gamma 5 gamma A d psi VA. Okay, plus delta d psi bar gamma 5 gamma A delta psi VA plus psi bar gamma 5 gamma a delta psi d a va. Here I've totally ignored the wedge symbols, okay, because it's too complicated. But I leave you as an exercise to put all the wedges here, okay? Whenever you see forms multiplied, wedges are understood. Of course, you have to be careful to when you switch the position of two forms, okay? Okay. Good. Then this equals twice delta psi bar gamma 5 gamma a d psi va minus delta psi bar gamma 5 gamma a psi dva. Okay? Okay. Now, delta psi on both terms is to the left. Okay? So we can simply drop it and write the equation, the field equation for psi. And we get gamma 5 gamma a d psi va equals 1/2 gamma 5 gamma a psi d va. Okay? This I write as 1/2 gamma 5 gamma a psi times t tilde a plus I kappa squared divided by 2 psi bar gamma a psi. I just rewritten d, the torsion, the true torsion, as the super torsion plus this bilinear term in psi. Okay? Now, there's a Firth identity, those you like a lot, I think, which you can easily prove, and is the following. Gamma a psi, psi bar gamma a psi, that is equal to 0. Okay? This is a Firth identity. There's wedges all around. The Firth identity you need to use is 1 for gamma mu psi gamma mu minus 1/8 psi bar gamma, call it a gamma ab psi gamma ab. Okay? Because these are the only currents which can exist between, well, in terms of size. Okay? Okay. Then if you use this Firth identity, then the last term cancels. You see, psi gamma a psi, psi bar gamma a psi. This is 0. We are left with this last one, which is gamma a d psi va equals gamma a half psi t tilde a. Okay? So let's now summarize all the field equations that we have computed so far. So this is the Rarita-Schwinger equation. Rarita-Schwinger equation. Okay? You may write it in components if you wish. Then we have the torsion, super torsion equation, and we also have r mu nu minus 1/2 g mu nu r equals minus kappa squared over E epsilon rho sigma delta mu psi bar rho gamma 5 gamma nu d sigma psi rho, so sigma, I think it's del sigma nu. delta nu sigma delta. Okay, that's all. These are the three equations. These are the three equations. Clearly, using this is 0. Okay. Yes. Yes. Of course, of course. General relativity is not supersymmetric, so that solution is not supersymmetric. Of course, you can have a theory with some symmetry. Okay, if you have a theory with some symmetry, in general, solutions will not have the same symmetry. Okay, that's common. So this is going to be a supersymmetric theory. Okay, solutions to the supersymmetric theory in general are not supersymmetric. Take the Schwarzschild solution. That's not supersymmetric. But then you can also find supersymmetric theory solutions. I guess not here, but in general. Okay. Consider in supergravity so-called BPS black holes. These are solutions which preserve a fraction of symmetries of the theory. Okay. Also here, you can take Minkowski vacuum. Okay. So in general, the theory can have vacua preserving all the symmetries. Okay. Now let's prove the supersymmetry of the action. Okay. So we want the action to be supersymmetric with respect to, invariant with respect to supersymmetry transformation. Supersymmetry transformation, we have characterized them as the gauge transformation of psi. Okay? Let's write them like this. One over kappa d epsilon. Okay? Why 1 over kappa? Because epsilon is the supersymmetry parameter. Supersymmetry parameter is defined to have a dimension of length to the 1/2. Length to the 1/2. Okay? Length to the 1/2. Psi has dimension length to the -1/2. So you need length to the -1. Which is 1 over kappa. Okay? Why length to the 1/2? Because we want that epsilon bar gamma a epsilon be a shift, a coordinate shift. Okay? So the square of two supersymmetry be a diffeomorphism. Okay? A space-time translation. Okay. So this is the way in which supersymmetry acts on psi. Now we have to devise supersymmetry transformation for all the other fields in order for this the whole action to be invariant. So we need to devise supersymmetry transformation for VA and omega AB. Okay? Omega AB. Now, and then require the variation, the off-shell variation, okay, of the Lagrangian to be 0. To be 0, okay? This, if we work in the first-order formalism, because first-order formalism, omega and VA are independent. So we have to separately invent transformation laws for omega AB and VA so that this is 0. Okay? Of course, if we were working in the second-order formalism, okay, then things would simplify. What we can do is the following. To check supersymmetry, what we can do is to work partially on shell. Partially on shell means in the so-called 1.5 order formalism. What does it mean, being partially on shell? We have seen that in the first order formalism, the super torsion equation, okay, is one of the field equations. Okay, we use only that one. We use only that one, so we are partially on shell. We use just one of the field equations, which is the field equations for omega, which is an auxiliary field, which is a non-dynamical field. We can use that. So we just impose TA tilde equals d TA tilde equals 0. We only use the super torsion equation. This implies that omega AB is a function of V and psi. Is a function of V and psi. Is no longer independent. Okay? So we are partially on shell. Why does this simplify our treatment? Simply because since we are partially on shell, delta L4 over delta omega AB is 0. The first term is nothing but the field equation for omega AB, namely the super torsion equation. Okay, so to check supersymmetry, we can simply neglect the first term and simply work with the second two. Okay, namely the variation of omega AB is not going to be independent of the variation of V and psi, and so we just need to work out the supersymmetry variation for V and psi. Then the variation for omega will follow from the super torsion equation. Originally, in the first work by Van Nieuwenhuizen, Friedman, and Ferrara, the check of the supersymmetry of the Lagrangian of pure supergravity, the one in 1976, okay, was done in the first order formalism. Okay, so they worked out omega AB, VA. They worked out the variation of the action with respect to all the fields. Okay, then later on, a few weeks later, Deser and Zumino came up with this smart trick, okay, which allowed them to only consider the variation with respect to VA and delta psi by choosing to be partially on shell. Okay, so this formulation was somehow simpler. Okay, it simplified all the proofs. Yes. Sorry? Well, actually here it's called 1.5 because we are not on shell, but it corresponds basically to, so we are on shell only with respect to omega AB. Okay, that's the way in which, so we are just partially on shell. We just set these equations equal to 0. Okay. Yes. Well, the second order in this case is basically is just this one basically. Okay, so you express omega in terms of all the other fields. Okay, it's just this one. So let us compute the variation of L4 with respect to psi. We are varying only the Rarita-Schwinger part. That's it. And this is equal to, now we use the property that d squared is proportional to the Riemann tensor, gamma A, gamma BC, epsilon, over kappa, RBC, VA. That is equal to minus I over 2 kappa epsilon ABC D psi bar gamma D epsilon RBC VA minus psi bar gamma 5 gamma C epsilon divided by kappa RAC VA. Okay? Here we just use the same trick to express this product of gammas as an epsilon times a gamma, okay? And then as a single gamma, okay? In terms of an eta AB times gamma C, anti-symmetrized in BC, okay? Okay, so next we use the super torsion equation, in particular the corresponding Bianchi identity, which should be satisfied, okay? And this implies that R AB wedge VB equals I kappa squared psi bar gamma A d psi. Okay? This is the super torsion equation, where we have set TA equals 0. Okay? TA and dTA equals 0. Okay? So, let's use this equation, and let's write this guy here as this, okay? So what we end up with is minus I over 2 kappa epsilon A, B, C, D psi bar gamma D epsilon R, B, C, VA plus I kappa psi bar gamma 5 gamma A epsilon psi bar gamma A d psi. Okay? Now we can simply switch the position of epsilon and psi for free. No, because this is an anti-symmetric, the C times this is an anti-symmetric matrix, right? So we can simply switch the position of the two with no change of sign. Okay, this is equal to then there is another property here, which gamma 5 gamma A, now you have to check, times psi bar gamma A d psi. This is equal to gamma A psi bar gamma 5 gamma A psi. There is this property here. How do you check this property? This you prove by using Firth's identity. You Firth this product psi bar, you just Firth it, okay, here, and you prove that the expression you get here, the expression you get here are just the same. Use the Firth identity I gave you earlier, okay, and then just prove that by Firthing this and this, the expressions you get here and here are just the same. Then the two are equal, okay? Okay. Now let's use this property, and then this allows us to take gamma 5 here, which is what we want. Okay, by using this property here. So here I get minus I over 2 kappa epsilon A, B, C, D psi bar gamma D epsilon R, BCVA, and then we have plus plus IK, I kappa, epsilon bar gamma A psi, and then here I get psi bar gamma 5 gamma A psi, d psi. Okay, we get this. Okay, we are almost there, because you see that this can be written as you can write this guy here as minus 1 over 2 kappa squared RAB VC I epsilon bar gamma D psi I kappa. Okay? Minus psi bar gamma 5 gamma A D psi I kappa epsilon bar gamma A psi. Okay? I've written this like this, just taking this on the other side, and this like this. Okay? But you see that this is nothing but minus delta V of L4. Take L4, vary it with respect to V. Okay? This is minus delta V L4, provided delta V con A is minus I kappa epsilon bar gamma A psi. Okay? There is an epsilon here, epsilon A, B, C, D, sorry. Okay? You easily see, because this is the variation minus the variation of VD in the Einstein-Hilbert term. Okay? And this is corresponding variation of VA in the Rarita-Schwinger term with a minus sign. Okay, so this simply means that whole action is invariant with respect to the following transformation properties. And then you deduce the transformation property for omega AB. Okay? Then you deduce the transformation property for omega AB under supersymmetry. Okay? We didn't need to use that because we were partially on shell. Okay? We were assuming that super torsion and its derivative were 0. Okay, now next exercise that we want to do, okay, so this the action we started from is invariant under supersymmetry. So it's consistent. Yes?
When we do this calculation, and we find that the action is invariant in this 1.5.
Yes.
Then it is implied that it is also invariant if we keep it
Omega independent. Of course, yes, yes, yes. Yes, it is invariant also if we add
special case, or it can be this
in general, yes, yes, yes. That is a general property, and indeed it is used for the construction of more complicated matter-coupled supergravities. Okay, you can also use that. Okay, because the equation for omega is just an algebraic one. Okay, so you can go partially on shell there, and then you will deduce then the variation, supersymmetry variation of omega from here. Okay, by if you want, requiring that this be supersymmetric. Okay. A way to see that this constraint is supersymmetric, if you want. No, that you cannot do. That you cannot do, because you cannot solve algebraically in omega. And then that will mean that omega is a dynamical field. But the fact that this is a supersymmetry covariant condition, okay, this is supersymmetry covariant condition, that follows from the fact that the super torsion, now remember the way in which we constructed it, okay, we constructed it as the curvature associated with the curvature associated with the Villebine in the local super Poincaré group, okay. And so its variation, okay, under any super Poincaré transformation, it's covariant under any super Poincaré transformations, okay, simply because it is the curvature associated with this local super Poincaré bundle that we have constructed on curved space-time, on curved superspace, actually, okay. Okay, so let us now, as last exercise, let us now check closure of supersymmetry, that supersymmetry closes correctly. How do we do that? Well, we take a field, okay, the fields, and we vary the commutator of two supersymmetry transformations. What do we expect? In general, and this is you should know also from global supersymmetry, okay, supersymmetry closes on the fields on shell. So while L4 is SUSY invariant off shell, SUSY closes on shell in general, okay? In particular, on the fermion fields, if we compute the commutator of two supersymmetries on psi, okay, we see that they don't close, they close modulo field equations, okay? However, this is not the case for VA, the Villebine, as we shall see, it simply closes off shell on the Villebine. Modulo local invariances of the action, okay? Let's check. So what do we expect if we commute two supersymmetry transformations? We want to commute a supersymmetry transformation with parameter 1 and 2. Okay? Remember, local supersymmetry transformations are generated by, in 4-spinor notation, by a generated form. Okay? So let's compute the commutator of two of these. Okay? So let's see what happens at the level of the algebra, of the superalgebra. What do we get? Well, this is minus 1/2, okay? Then we have epsilon 1 bar, commutator of Q and Q bar, epsilon 2. But this is, here we get a 2i, okay? So we have a minus I, epsilon 1 bar, gamma A, epsilon 2, okay? And then what do we get? We get gamma mu, d mu, okay? Or if you want, gamma A, PA. Huh? That is x naught mu, x naught A, PA. Where x naught A is a coordinate, space-time coordinate shift parameter, which is I epsilon 2 bar gamma A epsilon 1, and is anti-symmetric in 1, 2, okay? So what do we get what do we expect if we commute two supersymmetries and we use the passive description of this commutator? Delta 1 comma delta 2 on a field, generic field, we expect to find minus delta x naught phi in the passive description. Okay, remember what we said at the beginning. We expect to find a minus here. Okay, so let us compute this commutator on VA. VA, that is equal to twice delta 1, delta 2, anti-symmetrized in 1, 2, times VA. What is this? This is first compute delta 2. First compute delta 2. This is the passive description. We first compute delta 2, and then on the fields inside the expression of delta 2 vary with respect to 1. This is the prescription. So twice delta 1 times minus I kappa epsilon bar gamma A psi epsilon 2. Okay? Anti-symmetrized in 1 and 2. This is the prescription. Now we vary the fields inside this expression with respect to 1. Okay? The first supersymmetry. We get 1 over kappa, which cancels kappa, and we get minus 2i epsilon 2 bar gamma A d mu. There's a mu here, sorry. Okay, d mu psi. D mu epsilon 1. Anti-symmetrized in 1 and 2. Okay? What is this? This is equal to minus I epsilon 2 bar gamma A d mu epsilon 1 plus d mu epsilon 2 bar gamma A epsilon 1. Okay? Anti-symmetrized. But this is nothing but a total derivative. Minus A I d mu epsilon 2 bar gamma A epsilon 1. Okay? But this is minus d mu x naught A, what we called x naught A, right? X naught A. Okay? So, let us define x naught mu as VA mu x naught A. Okay? Like this.
How much longer are you planning on?
Oh, sorry. Okay, we can stop for half an hour, okay? And then we can resume, if you wish, in half an hour time, okay? Is it okay for you? Okay, thank you very much. Sorry. Okay. Okay. So let's resume from where we stopped. Let's finish this calculation. So we had written the anti-commutator of two supersymmetries on the Filbine as minus d mu x naught nu v nu a, where now x naught nu is a local parameter, right? Is a bilinear in the supersymmetry, in the two supersymmetry parameters. And this is minus d mu x naught nu, because there's no, this is the derivative part here, okay? V nu a minus x naught nu d mu v nu a, okay? Then there is the connection part. This has a connection, remember, as a connection, spin connection acting on the here, on this a. So we have minus omega mu ab x naught nu v nu a b, okay? Okay. So what is this? This is minus d mu x naught nu, okay, v nu a. Here I want to interchange these two indices. So I write this as the term with the two indices interchanged, okay, plus twice the commutator, twice the anti-symmetrization. So minus x naught nu d nu x mu a minus twice d mu v nu a minus omega mu ab x naught nu v nu a. Okay? Very good. Now I can use this, okay, and write it in terms of, oh, sorry, there is an x naught here, minus 2x naught. Nu. Write this in terms of the torsion, okay? Here we have a non-vanishing torsion. What is this? This is minus the diffeomorphism variation, infinitesimal diffeomorphism variation of V, the Filbine, okay, with x naught parameter, x naught mu parameter, okay? So this is minus delta x naught VA mu, okay? This is the general transformation property of the Filbine under an infinitesimal diffeomorphism with parameter x naught mu. What is this? Let's write it in terms of the torsion. This is plus x naught nu t nu mu a. This is the torsion. I wrote this in terms of the torsion. Now I have to subtract the connection part of the torsion, which is not here. Okay, so what we get is plus twice x naught nu omega mu ab vb nu, anti-symmetrized, in mu nu, minus omega mu a b x naught nu v nu b, okay, which is this term here. Okay, just written this in terms of the torsion. I get this. Now you see this is an antisymmetrization, and this cancels one of the two terms in this antisymmetrization. Mu nu minus nu mu, and this cancels one of them. So what we end up with is minus delta x naught v mu a plus x naught nu t nu mu a plus, sorry, minus x naught mu omega mu a b v nu b, okay, which is this one, okay. So you see, this is the term we expect from the closure, right, from the closure of two supersymmetries. But then we get some other terms, okay. We get some other terms. We get this term here. How do we interpret this one? This, you see, is a delta Lorentz of v mu b. Okay? Let's write nu mu. This is a Lorentz variation, local Lorentz variation of the Filbine. There's a local Lorentz variation with the parameter, which is this one, which depends on the connection. Okay? And how do we interpret the other one? The other term, x naught nu t nu mu a. How do we interpret this term? This term is nothing but, let's write the torsion. We know that torsion is non-vanishing. This is x naught nu times minus I kappa squared psi bar nu gamma a psi mu. Okay? This is minus I kappa squared x naught nu psi bar nu gamma a psi mu. Okay? But this is minus I kappa epsilon bar gamma a psi mu. So you see, this term here, which contains the torsion in the commutator of two supersymmetries on the Filbine, can be interpreted itself as an infinitesimal supersymmetry transformation with parameter epsilon bar, which is kappa x naught nu, which depends on the two supersymmetry parameters, remember, psi nu bar. Okay? So what happens is that supersymmetry closes the algebra modulo what? Modulo local symmetries of the theory. It closes because this is the term we would expect from the supersymmetry algebra. Okay? Modulo all the other local symmetries of the theories, which are Lorentz symmetry, which is a local symmetry, and supersymmetry. Okay, so modulo an extra supersymmetry and the Lorentz symmetry compensating transformations. Okay, this is quite common in even in globally supersymmetric theories, that supersymmetries close the algebra modulo local symmetries of the theory. If you remember, globally supersymmetric theories involving a vector field, okay, in the West-Zumino gauge, if you compute the anticommutator of two supersymmetries, and in a moment we are going to review that, if we compute the anticommutator of two supersymmetries on the vector fields, it closes the correct algebra. Okay, it closes. Minus delta x naught vector field plus an extra gauge transformation. Okay, so supersymmetry algebra closes modulo local symmetries of the theory. And that's fine. Here on the field bind, we didn't need to use field equations. But if we computed the commutator of two supersymmetries on the gravitino, then we would have needed the gravitino, the Rarita-Schwinger equations. Okay? Because supersymmetry close on the fields in general, only on shell, upon the use of field equations. Okay, let us now review the description of the Ves-Zumino term. Sorry, the Ves-Zumino multiplet and the vector multiplet. Okay, in a globally supersymmetric theory, and then couple it. This we will do the day after tomorrow. Couple it to gravity. Okay, so we will be able to construct explicitly a supergravity theory coupled to matter. Okay, then we will mention how this generalizes in the presence of a generic number of Ves-Zumino multiplet and vector multiplet. Okay, so Ves-Zumino multiplet. In the globally supersymmetric theory. Remember, the Ves-Zumino multiplet consists of a spin 1/2 field and the two scalars. The scalars I call A and B. Spin 1/2 field lambda. Okay? Okay. Lambda is Majorana. This is a scalar, and this is a pseudoscalar. Okay? So, the Lagrangian has this simple form, d mu A divided by 2 plus d mu B divided by 2 plus I divided by 4 lambda bar gamma d slash lambda. Okay? Very simple. Are you familiar with this? Okay. So, delta A equals epsilon bar lambda divided by 2. Delta B equals I epsilon bar gamma 5 lambda divided by 2. Okay? And delta lambda equals minus I d slash A plus I gamma 5b epsilon. Okay? That means that delta lambda bar is I epsilon bar d slash A minus I gamma 5b. Okay? Then you compute the variation of the Lagrangian under these supersymmetry transformations, and you verify that it is invariant. Okay? Up to a total derivative. Okay? So this I leave you to check, okay, where kappa mu is equal to 1 over 4 epsilon bar gamma mu d slash A plus I gamma 5b lambda. Okay? Clearly this is not 0. This we will need to compute. the coupling to gravity. First of all, the Noether current, supersymmetry Noether current, and then the coupling to gravity. This is going to be an important ingredient. Okay. Next, define Z as A plus IB. A and B naturally arrange, okay, in a single complex scalar. What happens if we do delta Z? Well, if we do delta Z, we end up with epsilon alpha lambda alpha in the two-spinor notation. Or if you want, epsilon bar dot lambda dot, where this means the upper component, okay? That is chiral component. Okay? This is the two-spinor notation, four-spinor notation. Okay? Now, delta gamma, delta lambda equals, then you simply rewrite this in terms of Z, and you easily verify that this is minus I d mu Z gamma mu epsilon bullet. Here they have opposite chirality. Okay? Okay, then delta lambda bar, that's I epsilon dot d slash Z. Okay. Now you see here that if we arrange A and B in a complex scalar, what happens is that it transforms in a chiral component of lambda. Okay, it transforms in a chiral component of lambda. Call it left hand component of lambda. Okay. So similarly, delta Z bar transforms in the opposite component, where lambda is 0, lambda bar alpha dot. Okay? Is the other way around. Lambda, delta lambda dot here is equal to minus I d slash Z bar epsilon dot here. Okay. Now you see that Z is precisely the lowest spin state of in our construction of the super multiplet, right? Simply because delta Z only contains epsilon upper half, which is Z minus I epsilon Q plus epsilon over square root of 2 Q. Okay, only contains the epsilon upper half part. This means that the commutator with Q lower bullet is 0, that is Z with Q bar alpha dot is 0. Okay, so Z is precisely the state which is annihilated by Q bar. And lambda is the state annihilated by Q. Q alpha. Okay, fine. If we compute the supersymmetry, the commutator of two supersymmetries on our fields, what do we get? Well, you check that this is precisely minus delta x naught lambda. Okay, so Z, that you can check easily. Okay, so that the supersymmetry variations close the right algebra. But then if you do the same calculation on lambda, that is on the super partner, what do you get? Well, you get minus delta x naught lambda, and this I invite you to check, minus I epsilon 1 upper bullet mu epsilon 2 lower bullet d gamma mu d slash z d slash lambda. Okay? You see, it doesn't close. It doesn't close. Because you have an extra term here. But then this extra term vanishes on shell, because the field equations is just this slash, the Dirac equation for a massless field, massless spinner, spin 1/2 field, okay, and that sets the second term to 0. So the commutator of two supersymmetries, okay, is a translation, okay, modulo field equations. They close the right algebra modulo field equation only on shell. In n equal to 1 supersymmetry, we can make supersymmetry close off shell, provided we add an extra field, as you know, provided we add an extra field, which is called auxiliary field. Supersymmetry closes off shell. Now, if we want supersymmetry to close off shell, how many auxiliary fields do we need? We need as many auxiliary fields, okay, as it is required from the matching, by the matching of bosonic and fermionic degrees of freedom off shell. So how many auxiliary fields are needed in order for the off shell degrees of freedom of the various fields in our multiplet to match? Well, off shell, we have Z, which are 2 bosonic, okay? We have lambda. Lambda off shell, how many degrees of freedom has? How many? Who says 2? Who says 4? Who says 5? Okay. Off shell, a spinner has 4 components, right? In 4 dimensions. So it's 4 fermionic components. 4 components. Then Dirac equation halves them to 2. Okay? So you have 4. Then how many bosonic degrees of freedom we need to match bosons and fermions? 2. So we need an extra complex scalar, which I call F plus Ig. 2 bosonic. And now we have a matching. So using this, okay, we can hope to close, and indeed this is the case, to close supersymmetry off shell. I just give you the results. I think these things you've already seen. You change your supersymmetry, the supersymmetry transformation law of your fermion, of your chiral fermion in this way, and then you add, by adding a term depending on this new complex scalar, then you define the supersymmetry variation of the complex scalar as follows. Okay? The supersymmetry variation of the scalar, or the physical scalar, Z, is the same as before. Okay? Then you modify the Lagrangian, like this. By adding F squared divided by 2. Clearly F is unphysical, is auxiliary. Okay? It's non-dynamical. And on shell, F equals 0 in this Lagrangian. Okay? On shell, on shell f is equals 0. This is consistent. On shell, we get back to the previous transformation property of lambda, f equals 0. Also, delta f is equal to 0 because on shell, p slash lambda is equal to 0 because that is the Dirac equation. Okay, so on shell everything is consistent, and we are back to our previous description. But what happens to the commutator now of you can check that this is indeed invariant. Okay. Yes, tell me.
Se ne stava andando.
Ah, te ne stai andando. What language is this?
Se ne stava andando, non vorrei... Ricordo registrato.
È tutto registrato. Scusate, let me stop because this is going to be recorded. Okay, then now you can check that delta 1, delta 2, lambda, the extra term in the commutator of two supersymmetries that we found in lambda now simply cancels out, and we get minus delta x naught lambda. Check. Okay. Very good. Now, let's do the vector multiplets, and then we stop for today, and then we go on next, the day after tomorrow, okay? This is just for recalling you some few things which you may need. We will need the day after tomorrow. First of all, now I want to describe the vector multiplet. So, chi d and a mu. This is the field content off shell of the vector multiplet. No. Actually, we have seen that the vector multiplets in n equal 1 just on shell, because we have constructed our states on shell, consists in 1 times a vector plus 1 times a spin 1/2. Okay? 2 bosonic degrees of freedom, 2 fermionic on shell. Okay? If we want to make the matching of bosonic and fermionic degrees of freedom off shell, we have to add an auxiliary field. How many auxiliary fields do we need? Well, off shell we have 4 fermionic degrees of freedom, okay? But off shell, remember, a mu has 3 bosonic, then we need 1 real scalar. Okay? Then we have the matching of bosonic and fermionic degrees of freedom on off shell, right? Okay, so L equals minus 1 over 4. That's the Maxwell action, usual Maxwell action, okay? Plus I over 4 chi bar d d slash chi plus d squared half. You see, d always enters just as before, no, in a without derivative, so that on shell d equals 0. Okay, delta mu, supersymmetry variation are minus I over 2, epsilon bar gamma mu chi, delta chi equals minus gamma mu nu, epsilon f mu nu, divided by 2, minus I gamma 5 epsilon d. You see, you have a d here, okay, in the supersymmetry variation of chi. Then we have delta d, which is equal to minus 1/2 epsilon bar gamma 5 d slash chi. And you see the variation of these proportional to the equation of motion, just as before, the equation of motion of the fermion. So that on shell, d is equal to 0, but consistently also its supersymmetry variation. And it is a general property of these auxiliary fields, F and D, that their supersymmetry variation is a global, is a total derivative. You see, this is a total derivative because epsilon is global now, is constant. Okay, so they vary as global, as total derivatives. Okay, this is important for the construction of the actions, supersymmetric actions. You can easily verify that this, well, it takes some computation, but you can verify that this action is supersymmetry invariant. If you have any problems, we can discuss it, okay? Yes?
We wrote 3 degrees of freedom for the
Yes.
I was wondering why it was not 4.
Not 4. Because one is one is gauge, okay?
But by means of gauge transformation, why can't we go to 2 then?
Sorry? No. Because sorry. One is the longitudinal mode. That is an invariance. That is an invariance of your field, right? So a mu, that's an off-shell invariance, right? In the Coulomb gauge, you're fixing this, but you, yes. In the Coulomb gauge, you have 3. Yes. In the Coulomb gauge, you set A naught equals 0, and you're left with AI, and that's 3.
But I also have divergence of AI.
Yeah. Okay. But that does not alter the number of degrees of freedom. Then the equation of motion reduces the yeah.
In the momentum space, it tells me that k dot ak equals to 0. So
Yes.
it means that there's no longitudinal.
Hold on. True. No. Sorry. You're saying that. Let me see. That. No. Sorry. Okay. This is just the gauge degree of freedom. Okay. I just so there's no longitudinal mode. That is precisely. But then what you the equations of motion will tell you is that you also have the only degrees, the only physical polarizations are those which are perpendicular to the direction of motion. Okay, so you have 2 polarizations. Okay, 2 independent polarizations. Is it true? So without anything, you just know that there is one function which is one component, if you want, which is in physical, okay, and that's 3, and that matches with the other components, right? Okay. Okay, so you verify that this is this is invariant modulo a total derivative, and you can compute the total derivative, okay? But the total derivative, after some work, you can compute it, and it is I over 8 epsilon bar gamma mu nu gamma sigma plus 4 eta sigma mu gamma nu chi f mu nu. Well, actually, we could also avoid this mu nu. this anti-symmetrization, plus 1 over 4 chi bar gamma sigma gamma 5 epsilon d. Okay? Okay, so this is the kappa mu, and you can see that d mu, kappa mu, is different from 0. That you can check. After some algebra, you can derive this expression of kappa mu. You can also verify that supersymmetry closes, but most importantly, delta 1, delta 2 a mu, this is equal to minus I epsilon 2 bar gamma nu epsilon 1 f nu mu. Okay? So you see that supersymmetry closes, okay, like this. Supersymmetry, two supersymmetry transformations, they satisfy this relation here. Now, this is just in part the closure we would expect. Okay? This. In part, this is d mu times I epsilon 2 bar gamma nu epsilon 1 d nu a. Sorry, d a nu. So you see here that this is minus delta x naught a mu plus delta lambda a mu. Supersymmetry closes modulo a gauge transformation on a mu, where the gauge parameter depends on the fields. So this is very similar to what we found before on the field bind. Supersymmetry close on the field bind modulo local symmetries of the theory. In this case, the only local symmetry of the theory is the gauge transformation on a mu. Lambda equals I epsilon 2 bar gamma nu lambda epsilon 1 a nu. Okay? And you see this parameter depends on the fields. Okay? Then you can verify with these transformation properties that supersymmetry close thanks to the auxiliary field. They close also on the spinor without need to use the supersymmetry transformation. Okay, sorry, the field equations. Okay, so one final thing, but I'll be fast. Is the super field description of these multiplets. Okay. Remember that our fields in superspace were defined by acting on the fields in terms of our coset representative, acting on the field at the origin. Okay? Like this. Now we can change our parametrization of superspace by defining L1, okay, the coset representative, in a different way. Okay, defining it like this. In this parametrization, where this is equal to L of x theta theta bar, and you can verify using the algebra that y mu is equal to x mu minus I theta sigma mu theta bar in the two-spinor notation. You can easily verify this. Now, in this parametrization, L1, you see that the representation of the supersymmetry parameter generator Q alpha is I d alpha. Q bar alpha dot is I d alpha dot plus 2 sigma bar mu theta alpha dot d mu. But most importantly, the super covariant derivative d bar alpha dot is equal to d alpha dot. So now this parameterization makes it simpler to derive the expression of chiral fields. You see, because chiral fields are defined by the condition that d alpha phi equals 0, which boils down to d alpha dot phi equals 0 on superspace. This means that phi in this parameterization simply does not depend on theta bar. So chiral is x theta theta bar, which is phi y theta. The dependence on theta bar can be reabsorbed in this y. That's it. And this expands as follows: z plus square root of 2 theta alpha lambda alpha plus f theta squared. And these are the fields we have just described. Okay? These are the fields you've just described. You can verify that the supersymmetry variation of this superfield gives us the correct variation of its components. That is the variation we wrote before of z lambda and f. Delta phi is equal to minus I over square root of 2 times epsilon alpha O of Q alpha plus epsilon bar alpha dot O of Q bar alpha dot. This is and times phi. Okay? And this gives you precisely delta z equals epsilon bar upper bullet lambda upper bullet delta lambda and so on, and delta f equals minus I epsilon bar upper bullet. Okay? That precisely gives you this. Okay? So everything is consistent. Clearly z q bar alpha dot, as we have said before, is 0, but it is also f q alpha is 0. Okay? Fine. But this is not the most general superfield. We have seen that the most general superfield is in general, well, the components of the most general superfield form a reducible representation of the super Poincare group. Okay? We can write the most general superfield how? Okay. 10 more minutes. Okay? The most general superfield has an expansion, which is rather complicated. And so on. It's plus plus theta squared, theta bar squared, divided by 2 d minus 1/2 c. Okay, in particular, it has this upper highest order component in theta. Okay, this is called the d term of the field, the superfield. We can impose reality condition on the superfield, okay, on a generic superfield, not on the chiral one, because then we would only get a constant field. Okay, we can impose this reality condition, and we can compute the variation, supersymmetry variation of V. And you can easily see from here, okay, that the last term, the highest, the term which is highest order in theta and theta bar, transforms with a total derivative. And this is important, okay, because this tells us that if we have a superfield V and we restrict to its highest component in theta and theta bar, okay, we can use that as a viable term in a supersymmetric Lagrangian. Namely, we can write a term in the supersymmetric Lagrangian like this. Okay, the supersymmetric action like this, because this term here, which is called the d term, varies through supersymmetry by means of a total derivative. Okay, and therefore the corresponding term is invariant under supersymmetry. Okay. Fine. What does V contain? How many fields do V contain? V contain a lot of fields. Okay. In particular, it contains, well, it contains chi, A mu, and D. The fields of the vector multiplet that we have, off-shell vector multiplet that we have defined before, okay, plus other fields, which are C plus, M plus IN, and then we also have an extra spinner, okay, an extra spinner. And if you sum, then we have C. If you check, these are 8 bosonic plus 8 fermionic, where now A mu is counted as 4. Okay? But this is 4 bosonic plus 4 fermionic plus 4 bosonic plus 4 fermionic. Okay? This has the degrees of freedom of our vector multiplet, of shell, of course, and extra degrees of freedom, which are arranged in a chiral multiplet, in a chiral West-Zumino multiplet. Okay? And these are gauge degrees of freedom. So what happens is that these degrees of freedom here of a generic real superfield in 4 dimensions comprise degrees of freedom of a vector multiplet plus degrees of freedom of a chiral multiplet, which encodes the gauge degrees of freedom. Okay, the gauge degrees of freedom. And that's all. So we can give a superfield description of our vector multiplet, and we stop here, taking a real superfield V, okay, taking a real superfield V, and computing it. Okay? And you can easily see, because there's a d squared here, okay, that d bar alpha dot w alpha is equal to 0. Okay? You can compute directly. There is also these properties hold. Okay? Also these properties hold. And you can easily see that minus 1/4 dx squared d for x w alpha theta squared component, so just the f term part of this chiral superfield, only the f term part, okay, plus Hermitian conjugate. This is nothing but the action we have written before. Okay? You get precisely this. Okay, well, that's enough for today. The day after tomorrow we are going to use this and to couple supergravity to matter, okay? Using the Noether method. That's enough. Thank you very much.